Okay, well, good afternoon, everyone. It's a pleasure to kick off the mineral physics portion of the CIDER program. So I wanted to thank the organizers for giving me this opportunity. And please feel free to interrupt as I go forward, and also all of these slides will be available. I'd like to acknowledge a PhD student that's working with me, Natalia Solomatova, who was heavily engaged in the creation of this presentation. And right now she's at Goldschmidt, so she is presenting her work with myself and Paul Asimov there. And you'll see Goldschmidt come up a little bit later here in the talk. So what I'm really excited about is many things, but the individuality of all of these phases and minerals, basically, that make up our planet. So each phase inside of the Earth has its own personality, and this is dictated by essentially the atoms and the arrangements that make up the phase, and also dictated by thermodynamics. Right? So in terms of an equilibrium assemblage, one goes towards the lowest energy. And what I show here are just a few snapshots of some of the major players, either in dynamics or in sort of interpretation of Earth's history. That includes a mineral inclusion that has a significant hydration component to it in diamond. Bridgmanite, which is a major silicate in Earth's lower mantle, that only just received its name last year when it was found in a meteorite and described by Oliver Chauner and his colleagues. And San Carlos olivine, which is a lower pressure assemblage, what we think makes up, or at least describes, a primitive upper mantle of the Earth that contains olivine, and depending on the pressure, can include garnet and pyroxenes. And what I also show here is the cleft segment of the Juan de Fuca Ridge, which is an active spreading area, and so which demonstrates that at least one example that the Earth is extremely dynamic, active, and melting, and that these processes could be occurring throughout the entire Earth's interior, and that those processes are dictated by the individual components in their assemblages that are stable at deeper depths. So a brief outline of the talk is, the tutorial is really just to do a basic overview of compositional constraints. These will be covered in more depth in the geochemistry tutorials. And building minerals and coordination environments, essentially what are the common coordination environments? Again, these are the building blocks of the planet. And individually, they have their own distinct properties that can then essentially dictate the entire behavior of the planet, which includes flow. And substitution mechanisms, so these are, I can use that, or the bamboo stick. And so some substitution mechanisms, which is a common phenomena in lower pressure mineral phases, and two-component phase diagrams, including partial melting. So essentially, this is to get everyone on the same page and even keel of major mineral phases, their coordination environments, and their phase diagrams. Okay, so a basic compositional constraints do come from observations of our sun. So in terms of the terrestrial planets, we have some constraints because we can observe the compositional spectrum of the sun. Now the details, so again, I'm not going to go into all of the details of the individual elements and what constrains each proportion, because those are still a subject of great discussion in the community. And we saw earlier in Matt Jackson's talk about the coal is super deep. So essentially the deepest drill hole is only about 12.262 kilometers. Actually, there's a slightly deeper hole, but this is more horizontal, so it's a little bit cheating. So this is one of the deepest vertical depths, and compared to 6,000 and change kilometers of the radius of the Earth, this is really just a pinprick. And so how do we then gain a foundation and essentially an understanding of what could possibly be stable at deeper parts of the planet, which again can control the dynamics, their behaviors. And so going deeper, one can look at mantle xenoliths, San Carlos olivine, for example. These are snapshots of primitive parts of the mantle before they've been partially melted. So we'll get into that in a little bit. And some primitive meteorites as well as pallasites, which have been differentiated, the core mantle boundaries of smaller planetary bodies. And going deeper in terms of remote techniques, of course, seismology probes the mantle at very high spatial resolutions. Of course, depending on the region of the interior of the planet, it can be extremely high spatial resolutions. And experimental methods, such as large volume apparatus, a piston cylinder, or multi-anvil press. Then going smaller into the diamond anvil cell regime, which can access multi-megabar pressures, thus trying to tap into the phase equilibria deep in the mantle, the base of the mantle, and the core, at least in terms of the Earth, and the theory and experiments that complement and also guide some of the experiments that are done. So in terms of element distributions, I've simply just highlighted some of the major elements and fractionated it to the weight in the crust and the weight sort of whole Earth approximation. Of course, these are approximations because, again, as we're discussing this morning, it's not completely settled whether the Earth is chondritic, for example. And so that can dictate the relative abundances of things like the magnesium content, the magnesium-silicon ratio, for example, which, depending on that ratio, that could essentially could produce a more viscous lower mantle, just for example. And so that will, so in terms of understanding that part, the details of the individual elements that will also, again, be discussed more in more detail in the geochemistry talks. I put a few of the oxidation states of iron that are commonly observed. There is a recent suggestion that it could exist as 4+. That is controversial, of course, that is something of current interest in how the oxidation state of iron varies with depth and hydration, the presence of hydration. And of course, where these elements reside then dictates the behavior of the materials. And so I'll go into some examples. There, just for example, yeah.
What's an example of a mineral that would have iron more than 3+?
There's a suggestion that iron hydroxide, when subducted down to core mantle boundary conditions, can disassociate and essentially free up the hydrogen atoms, leaving FeO2 as one of the products, which would... And right, yes. Mm-hmm. So in the crust, we have a very commonly thought assemblage of minerals, mostly dominated by the feldspars, more than 50% of the crust, and including the nesosilicates, which are garnets and olivine structures, and pyroxenes, quartz, micas, amphiboles, and we'll go through a few of these examples just to show what those minerals in terms of their internal structure look like. And I want to emphasize that it's in terms of crystalline, in terms of the solid materials, the crystalline materials, of course, have a lower free energy than their amorphous or, let's say, glassy counterparts. And it's a competition between the attractive, the binding forces, and the repulsive forces. And so these are dictated by essentially the forces between the atoms, the charges, and we'll go through some of those examples in just a minute. And this can be determined experimentally, typically using X-ray diffraction or neutron diffraction. It's mostly for the bulk material. Surface type probes include transmission electron microscopy, atomic force microscopy, electronic backscattering diffraction. But there really is no perfect crystal that exists. I think the closest thing is silicon. So you may have seen, sometimes one can see these huge chunks of silicon that can make them essentially boulder-sized quantities with far less than 1% of vacancies. And that's essentially why they can be used as optical devices. They're essentially used to monochromate X-rays, just for example. But there's really no perfect crystal exists. And this is also an exciting area because at any point in time, the structure of the material is just a snapshot of those atomic positions. Really, these atoms have a certain, neighborhood that they occupy. So they have vibrational properties. Those define part of the stability, the vibrational thermodynamics. And many of these phases, especially at low pressure in the crustal areas, have defects. They simply crystallize out, and in that particular environment, they have voids in their crystal structure. And how those defects change with compression is also a focus of sort of interdisciplinary research because it guides essentially how materials can flow. And we'll also see more details about, we'll have more discussion about rheology next week. And later this week, there'll be more focused talks on elasticity and equations of state. And so in this presentation, I'm going to go through some of these common bonding environments. These are, in terms of crustal materials, we have the linear arrangement, triangular arrangement, tetrahedral, octahedral, cubic. Some examples, of course, is a common carbonate phase, the calcite, which is characterized by this triangular arrangement. And then you can imagine that as we go into larger coordinations, that we also have very different environments. So in the quartz system, it's essentially described as an interconnected network. And why this is stable or not stable, that is touched upon in some of the rules that we'll go into, Pauline's rules, for example. And in Periclase or in olivine or pyroxene, the common coordination number of magnesium is an octahedral environment. Now, as soon as a transition metal goes into that octahedral environment, it will distort it, and it will distort it in, it's described as the Jahn-Teller distortion. Now, that distortion, we'll see, has a large effect on physical properties of materials, and that's expressed in spin crossovers, where the iron atoms will change from a high spin state to a low spin state. Now we'll give an example of that a little bit later, but yes?
What are the black triangle and the dashed triangle on the NGO diagram?
Just inboard and outboard.
What does that mean?
As a three-dimensional object. Yeah, in and out. Right, yeah, in and out. So we have something like this in 3 dimensions. And as soon as a transition metal ion comes in there, a cation comes in there, the unfilled d electrons favor a elongated section of this octahedron, which makes a Jahn-Teller distortion that essentially deviates from a cubic symmetry. And so it's essentially not perfect cubic symmetry, which can lead to some very interesting behaviors as that symmetry changes. And that's what we'll see in a few minutes. So in these systems, we have a common classification for tetrahedral coordinations and in isolated tetrahedrons common in olivine and garnets. Now, if they tend to share corners, they can go into double tetrahedra, chains or double chains, and essentially an infinite network and a sheet structure. So what we'll see is sort of an interesting arrangement of these tetrahedra as we compress the common phases. For example, in olivine, we start out with an isolated tetrahedral network. And at higher compressions, those tetrahedra tend to, what we'll see is that they'll go into share corners and an infinite network in the Bridgmanite structure. And so having these specific arrangements of atoms, we can see already that it could lead to anisotropic behavior. And so the forces that are acting on these atoms, which are expressed as bonds, you can imagine in a chain structure that this could result in, say, higher forces along the chain and perhaps weaker forces perpendicular to the chain. And this is also, we see this in the sheet silicates, where within the chain, it's a very strong material, like graphite, for example. Bridgmanite is also another example of this sheet-like silicate. And perpendicular to this sheet are extremely weak bonds, relatively speaking. In post-Bridgmanite, they are still quite strong, though. In the post-Bridgmanite structure, even though it's characterized as a sheet structure, the bonding environments are still quite, they're anisotropic, but they're not as anisotropic as, let's say, graphite or a mica. It's a highly compressed and dense form of a sheet silicate. Oh, yeah.
Should it not still be called post-perovskite if you refer to the structure as a...
Yeah, can call it post.
Yeah, I'm just curious about this. Like, are we supposed to call it post-Bridgmanite or post-perovskite?
I think post, because it doesn't have a natural observed counterpart, then it should still have the name post-perovskite. That causes some... But the calcium silicate phase, just as an aside, which we'll get to, does not have a natural analog, so that's still referred to as calcium perovskite. But I think that for Bridgmanite, there's some discussion whether you can call it post-Bridgmanite or post-perovskite. It's like calcium chloride. It's like the Stishovite phase. Yeah. Yes.
But there are potentially, since perovskite is a structure family that has many, many, many compounds in it, it actually is more accurate to portray it as post-Bridgmanite because that actually specifies it's the magnesium iron silicate. Just my opinion.
It does, yeah.
There
would
could be potentially many post-perovskites, like potassium tantalate has a totally different structure, but never mind.
Exactly. But it does refer to the magnesium silicate phase. There are still a lot of discussions about what that symmetry is for post-Bridgmanite or post-perovskite. We can refer to it. So I don't have a very strong opinion on this particular topic, but but the international mineralogical community does, and they would stubbornly still call that post-perovskite because there is no natural analog. But you should be on their panel.
Of the mineral per se. It's not a mineral name.
It's a structural. It's a structural transition.
It's a structure. It's a designation of something that is after the MgFeSiO3 phase. So
But it.
No, because you also have it with different compositions as a calcium
iridate, yeah. But it can also be it can also be before if you think of
Can we move on because
yeah.
I don't excuse me. I don't want people to get the wrong impression and think that this is one of the most exciting areas right now in mineral physics, discussing the name of our potential lowermost mantle. Nor is it pedagogically important.
Right.
Call it what you want.
Thank you. All right. So moving on, we will just briefly go through these symmetry environments. So this is a very common set of terminology that mineral physicists use to describe materials and their different phases. And so although there are 14 different Bravais lattices, I will just focus on a few of the very symmetric ones, cubic and hexagonal. From those systems, you can distort the structure in ways that are, of course, important for understanding their physical properties. But in terms of our discussion, I'll just give examples of the cubic and hexagonal systems. In the posted notes, I'll provide all of them. So in the cubic system, there are 3 different ways of classifying a cubic system. So primitive simple cubic, which is quite rare, actually, a body-centered cubic and a face-centered cubic. This is where the atoms reside, as you can imagine, on the faces of the cubes. And if we look at them in 3 dimensions, we have the simple cubic, again, body-centered cubic, which is a common structure for a low-pressure phase of iron, and the face-centered cubic, the FCC, is a high-temperature phase of iron. In the primitive cubic system, it is quite rare because the packing efficiency is not very efficient. And so one example is polonium metal. This is more for just demonstration purposes. It's not a common structure in minerals or alloys. In a simple cubic system, when you have more than one element, we do have these sort of interpenetrating cubes. And one example is the cesium chloride. And in body-centered cubic, the common mineral that we think of on the Earth's surface is metallic iron. It's BCC. Okay, so this is also quite interesting because it is cubic, but we also know that it is magnetic, right? And so having a magnetism, and actually it has a pretty significant magnetic field at the iron site, means that it is not exactly cubic. Locally, there is some distortion which gives rise to a magnetic field. And for face-centered cubic, of course, rock salt, halite, table salt is a primo example of this structure. But also iron at high temperatures will adopt the FCC structure at relatively low pressures. Yes?
If you go back one slide, you said because it has a strong magnetic field at the body center, at the center of the cube, we know that it is not perfectly cubic. Can you help me through that reasoning?
Yeah, at each iron site, exactly. Not to be confused with just the center.
Okay.
So at each iron site, there is about a few tens of Tesla, if one measures it with, let's say, Mossbauer spectroscopy of a field that has a particular angle with its crystal structure. So the magnetic structure, which is defined by the field strength and its orientation with the other these vertical planes and cube diagonal planes, is actually a slightly different symmetry environment. And so so in this case for BCC iron, we see that if this were in a magnetic field, that we would be able to measure a distinct, what's called the magnetic phase angle, and that angle is slightly different than these 90-degree angles that define the cube. So there's a magnetic structure that's essentially embedded in the so-called static structure. This is also the case for magnetite, for example. It has a very clear static structure of the atoms, but within the iron sublattice, it defines a different symmetry, which allows for a relatively weak field, but it is observable. I mean, that's, yeah.
Okay, thank you.
Sure.
Can I just follow up super briefly? I guess maybe Ved's question was something to the effect that there's symmetry in that crystal structure. And so why doesn't the effect of each atom on the other, through magnetic torques or whatever, balance, and so there's no net distortion? Because we look at that picture and there's symmetry everywhere.
Right.
And so you'd expect the magnetic influences to retain that symmetry.
Right. So
it's a reversible interaction, right?
Yes. So in a random orientation of iron atoms, or with BCC iron, we see that the field is relatively uniform, and so if one sort of if one aligns it either with a preferred stress or a non-hydrostatic stress tensor, then one starts to see these alignments and a slight deviation from cubic symmetry. Otherwise, for all intents and purposes, it does average out, but in any particular direction, it can be very strong. So it's like elastic anisotropy. So in cubic phases, we can see that there is a strong preference for stiff directions in the bonds versus weaker directions in the bonds. So the magnetic field is a tensor, and so it does not need to be uniform.
Yeah, maybe you should just add this is only for low temperature, up to the Curie point. Above it, it is perfectly cubic.
Right, it is perfectly cubic above the Curie temperature. So in that case, you have magnetic relaxations, and for different minerals, you have different Curie temperatures. So this is another subject of great interest. So moving forward, we can go quickly through this is the face-centered cubic. This is a common structure for higher temperature iron. This is the example where there is no magnetic field, as Rudy just pointed out. So, but the interesting thing I give the example of sphalerite here to show this nice hand sample. But in terms of FCC iron, the crystal structure transition is measurably several tens of Kelvin different than the magnetic phase transition. And so there is, there's this magnetic term that is, needs to be added to the free energy, and that term is sort of lingering on as the material is raised to higher temperatures. Okay. Okay, so moving through the cubic system, the example that is commonly used in deep earth mineral physics discussion is the Periclase structure, the Periclase-Wüstite solid solution. And so in the earth, the phase equilibria studies have put the ferropericlase composition at anywhere between about 10 to 30%, depending on what is coexisting, what other phase is coexisting with that phase. And there are suggestions that this can be a significant component either at the base of the mantle or in the core, very iron-rich concentrations. So, but this is the starting symmetry. Essentially, B1, it's also a terminology used in our community, but it's essentially the rock salt structure, and we have a face-centered cubic arrangement. And the other example I wanted to show is the hexagonal system. So the hexagonal system nicely describes a common phase that we observe at the surface of the Earth, quartz, and down to some minor compressions and temperatures as a network structure. But it also describes the most abundant phase in the core. So iron, and what's thought for most of the iron-rich alloys is that it's thought to crystallize in the HCP phase. And the HCP phase is a very specific stacking arrangement of the iron atoms. We can think of these, I'll go through this in just a minute, as essentially one of the most efficient ways to pack a structure. An FCC arrangement, which we were just looking at, one has a third type of stacking arrangement, which, in terms of large compressions, it's not as favorable because the more, at least at high compressions, because this leads to more degrees of freedom. Now, this is why that's why this is favored at high temperatures, because you do have more degrees of freedom here. And so going through, there's a few examples of some of the, the elemental metals, beryllium, magnesium, zinc. They commonly crystallize in this hexagonal close packing, as well as cobalt. So sometimes they're used as analogs to the main phase in the core, because at least up to now it's not possible to crystallize the HCP phase of iron at room pressure and temperature conditions. So a few schematics of these different packing arrangements, the HCP and the FCC phase. And going further, we can see that in the HCP structure that we have, again, because we're going A, B, A, B, A, that leads to a more efficient arrangement of the atoms. There are less interstitial sites. And so what do I mean by interstitial sites? We can see that in the AC environment, there's an octahedral hole. So this is where elements could reside in those holes. But you can imagine that at larger and larger compressions that becomes unfavorable. But something that is,
So these two packets, they have identical packing efficiencies mathematically, right?
Yes. Yes, but, okay. Yeah, so the question or the comment is that, yes, the FCC and the HCP structural arrangements and the layering, they have the same packing efficiency mathematically. But if one looks at the free energies associated with those arrangements, we also consider entropy. And when we have, in this arrangement here, in the hexagonal close packed system, we have a more favorable arrangement for the iron atoms than in the FCC phase, in this different stacking arrangement. But yes, mathematically they have the same packing efficiency, but they have different entropies. Okay, so when do different elements form solid solutions with other elements in mineral systems? I mean, there are some guidelines for this process. It's not really a free-for-all. And Pauline outlined this in great detail, and I think it's still, well, it's fairly well reproduced, and I would like to just show 4 of them. There's actually a 5th one, parsimony. In the radius ratio argument is that the cations are generally smaller than the anions, so we begin with this radius ratio of 1. Okay, but only cations that are large enough to not rattle around in the interstitials, but small enough to fit in. So it really does need to be a sweet spot of the size. Can't rattle too much. And so we have these schematic representations and then a more quantitative table later on. And we have an unstable limit where you see this cation would just be rattling in its cage. And now this could be stabilized in a very, very tiny space of pressure and temperature, such as you can imagine, zeolite structures, which are very open networks, they tend to absorb some of these cations, like cesium. That's a common void occupier. And in going through some of the different examples, we can see that based on some of these environments that we discussed earlier, one can use these radius ratios as guidelines to whether a certain element will exchange with another element or form a bond. And so I've just given a list of these elements. I won't go through. I'll leave those just for reference. And we'll go through with the electrostatic valency principle, and this has to do with the bond strength being proportional to the cation charge and the coordination number. And going through the interconnectivity, the sharing of the polyhedral corners and edges, this is something that folks have seen a lot of examples in a basic mineralogy class, and that as one starts to share more surfaces, it does become unfavorable because we're losing degrees of freedom. We have one can imagine the isolated tetrahedra over here, which is characteristic of olivines and garnets, going to corner sharing, and edge sharing is really not favorable. And so it is extremely unlikely to find this. One might be able to push a structure into this state perhaps kinetically, but thermodynamically it's really an unfavored arrangement, and especially the phase sharing arrangement. Okay, and the crystals containing different cations, this is one of the most prevalent topics in terms of discussing different phases that comprise the rocks that we observe at various depths in the Earth, is that of course these are not pure end-member phases that we observe in the Earth. It is not favorable to form pure magnesium end-member olivine. It's not favorable to form pure FeO. There is going to be some mixing. And in terms of the guidelines, or what are the sort of the traffic rules for this, they do still need to be relatively similar in size and relatively similar in charge. And a few examples I give are the potassium, sodium, calcium substitutions. This is very common in the Feldspars. The manganese, iron, magnesium, and iron 3+. These are very common in the refractory phases like olivine, pyroxenes, the MgO, FeO solid solution. And even the substitution of iron 3+ and aluminum 3+ is common, and it's thought to be the dominant substitution in the lower mantle when we have bridgmanite in the presence of garnet, which is the aluminum, which is delivering the aluminum to the system. And something to also consider is that the effective charge on anion size. So I'll give the example of sulfur. See, from 2- to 6+ is a significant change in the size. So this helps to dictate what the oxidation state of sulfur will be stabilized in which particular arrangement. And the same is so we can think of we can think of the effective pressure for silicon. Of course, at low pressures we have tetrahedral coordination, moving towards octahedral coordination in the transition zone and lower mantle, and the garnet phases do contain the cubic coordination of silicon. And going quickly through Goldschmidt's rules, this is and going on right now, the Goldschmidt conference in Japan, is this notion that Goldschmidt presented of the similar size and essentially the ionic behavior. And so I'll go quickly through this. And that the iron 2+, iron 3+ is common, so we can think of this in terms of Pauline's rules of the size. And you can also think of what are the cases that are not likely, the sodium and aluminum 3+, which are extremely unlikely.
Jennifer, I have a question. I guess it's about combined Pauling's rules and Goldschmidt rules.
Mm-hmm.
So a lot of the kind of rules that predict, the types of minerals that we see and the diversity that we see are based on very large differences in ion sizes. And so I guess my question is as you go to really high pressures, like in the deep mantle, do the ions share that same very large size distribution, or are they closer together in size? And if so, does that mean that the rules for deep Earth structures are maybe a little different from Pauling's rules, or maybe some of the rules become more important or less important? And does it mean that maybe there's less of a diversity in the deep Earth compared to the surface?
Yeah, I think it's the latter, that because of compression, the sizes do become similar. So the rules can still be applied. And so that leads us to understand some of these systems that have been calculated or observed experimentally, that there can be more exchange of elements, of different types of elements that we wouldn't normally think of in the upper mantle or crustal conditions. So sodium and calcium, which are normally not as favorable to, let's say, to enter the bridgmanite phase, could become favorable. It depends on also what's coexisting with that phase. Right? The calcium silicate perovskite structure does have a larger cation area to perhaps accommodate some sodium if there's some basaltic or sediment components that are being subducted into the mantle. So I think we should not be limited by the behavior of minerals at the surface of the Earth, but that those rules are still applicable because they do.
So what she's saying that under higher pressure, the cation side will become similar.
Yes. Well, so if we look at the size of the silicon, let's just as an example, this is a schematic. This relative size will then be similar to the aluminum and iron and perhaps magnesium and calcium. Now, what would need to be done is just to compare this with single crystal X-ray diffraction measurements, which do sort of put constraints on these sizes. that's how one constrains the size distributions. Yes.
Yes, but all these rules actually works when we consider a model of atom which is a hard sphere. We only consider a hard sphere model for atom. In a crystal, the electron density is more diverse than just a sphere around the atom. So
for sure.
That's why we have several cases in which we can't apply these rules. Yeah.
Right.
But that hard sphere model with additions works really, really well in many, many cases.
Especially for the liquids. But for solids, sometimes it's much more complicated.
Yeah, that's true. So these are, these are basic guidelines that can also put some constraints on how we try to put together the planet, because it's really not. There are some considerations that that hold at any compression. If there are similar sizes, they could be favorable to exchange with each other. So that's really something to still consider. And also at higher temperatures, there is the contribution from entropy allows for more of this mixing general. It's, getting above 6,000 Kelvin, there is significant probability that many of the elements will, say, alloy into iron, for example. This is an argument that is used for the case of the magnesium dissolution into the core. It's not really magnesium per se. It's a small amount of, essentially, it's something that is not that abundant, so magnesium was chosen. One could make the argument, and the results wouldn't change that much for, say, calcium or aluminum. Okay, so in the coupled, so we've gone through the coupled substitution. So I will go through this relatively fast. For the calcium and aluminum, these are favorable in terms of exchanging with each other. With sodium, it's similar to sodium and silicon. The albite anorthite solid solution that I'd like to go through to show some examples of that solid solution and of melting. And so coupled substitution is also the nice example of corundum and ilmenite, that these two end members can easily form a solid solution using the substitution of iron and titanium for aluminum. And with the iron sulfide system, we'll also see that there are situations where the sulfur does become more oxidized, and in that case, in this particular structure, vacancies are formed in order to balance the charge. So I have a few examples of that. And with the interstitial sites, you can imagine this is a common zeolite-like structure where it has very large empty cages. And the charge balance can be maintained by putting a small amount of cations that are essentially just balancing the charge, but are of similar size that can fit in there, but they don't rattle around too much. And so this can also facilitate ion exchange, where the network remains intact, but the elements that are residing in the cages could be easily exchanged. This is common in some of these heavy elements, strontium, cesium, and it's used for nuclear waste remediation, for example, or at least in the thought that it could absorb some of those nasty cations by sticking them into a zeolite.
Jennifer, can you remind us what you mean when you say oxidized? Does that mean that the charge goes up? And you said sulfur gets more oxidized.
Yeah, so it has to be balanced with either in the neighborhood of when it becomes oxidized, it loses an electron, so that electron has to go somewhere. So either it goes into another phase, that, like iron metal, for example, in the case of iron being oxidized, or it could be that the partial pressure of oxygen in the whole assemblage changes. And so that's another aspect that's not touched upon in this talk, but perhaps in in the geochemistry discussions, is that environment, the oxygen environment. This is discussed as in terms of Earth's history, there, of course, is a major change in the oxygen content of the atmosphere, and how that is expressed in the deeper parts of the planet, and is there any evidence that we have for that change? Or a smoking gun, I should say. Okay, so the next series of slides, I wanted to just briefly go through a two-component phase diagram. This is a similar, this can be applied to all solid solutions that are two-component end members. And some of you probably have seen this before, and this case is just really to bring everyone up to speed on what is meant when we're going through these processes, because the Earth did not just crystallize out of a melt and it's a single composition. There's a whole process of melting and remelting, and what does that mean when the residual phase is different than the starting liquid? And so in a two-component system like the albite anorthite system, in a phase diagram, this is just a two-component system. Now these are really, can be expressed in n dimensions. So I want to really just do a two-component system here to simplify it. And so we have, let's go in here. So we have the all-solid region, the all-liquid region, and of course the region in between is the liquid and crystal. And the melting point of the sodium end member, which is the lower, it's not as refractory as the anorthite, has a lower melting point than the end member anorthite, calcium end member. And in going through this, in between the two, of course, is the loop that defines the coexistence of the solid and the liquid. And so any composition in between this will not have a single melting point. And so we have the liquidus that defines the line that separates the liquid and the liquid plus solid. Okay, so if we start with a composition that is 30% anorthite, and we lower the temperature as we go into this loop, we now start to encounter two different types of chemistries that are defined by the lever rule, which I show in the next slide. And so this composition here, if we were to look at that, take a snapshot of it, let's say experimentally, just quench that, we would find that we would have crystals that are 55% anorthite and 15% albite. Now, what are the proportions? Those are determined by the lever rule. The melt fraction be defined by this area here, this line, it's a line, relative to the total line. And so this is we'll also see that this process here, if this continues and nothing disturbs the system, we have the equilibrium melting or equilibrium crystallization. And so there are essentially two types. I've generalized them into equilibrium melting and fractional crystallization. This isn't necessarily just happening near the surface of the planet to create mid-oceanic ridge basalt. It could be happening at all depths, depending on where the geotherm intersects the solidus of the whole system. And so in doing the equilibrium crystallization, one can use the same terminology as just crystallizing instead of melting. And for the equilibrium crystallization, we start with, let's say, a 70% anorthite, and we're not disturbing the system. So we go through the process of observing melts and crystals. So this can be applied to any system, right? Of course, in n dimensions, it becomes a lot more complicated, but the math is there. There's something. There are, of course, experimental constraints that do make this difficult to determine all of those terms in the n-component system, but it's a tractable problem. And so in any system, when you have some melting, we talk about systems in the Earth, LLSVPs, ultra-low velocity zones, subducted slabs, sediments. There's discussion about whether or not they create or they permit partial melting to happen. That means the chemistry is going to change if it is not an equilibrium process. And so in an equilibrium process, we just march through, and the proportions at any snapshot in time in the binary loop are, again, dictated by the lever rule. But if it's not disturbed, it just crystallizes out at the same composition. But the Earth is dynamic, and it's very likely that some of this melt will be extracted, and that crystals will separate out. And so when they separate out, if the crystals then start to sink, which we see clear examples of this, even in the Skaergaard inclusion that Quentin showed earlier, and the Palisades Hill, is beautiful examples of this, is that the crystals sink. So they're separated out from this whole system. And when they sink, they then define a different composition of the melt. And this composition evolves through the loop as the different compositions of the crystals sink because they are denser, and we move down defined by essentially the lever rule at each step, how much proportion and which what composition is the melt and what composition is the solid. And so in this particular example, the last materials to crystallize are the very sodium-rich, close to the sodium-rich end member, albite. And that's observed in some of these systems. This is a very, obviously this is a cartoon image, but one can imagine this situation, and it's not necessarily just happening at the surface of the Earth. And this defines Bowen's reaction series, which is a common sort of way to think about how minerals crystallize out at minerals that are under relatively low compressions. And so this continuous series was what I just showed an example of, the calcium-rich plagioclase, which is very refractive, going down to the anorthite sodium plagioclase. In the system of olivine to biotite, this is a discontinuous series because this is not a simple two-phase system. There are interruptions of the phase diagram as eutectics and peritectics, and that will separate out a system it will not evolve through one continuous loop. It will jump around to the other loops. And so in examples at the surface of the Earth, we have a very nice field observation of the dense, highly refractive crystals sinking down to the base of this fill. I mean, this was there is some basalt at the bottom here because it cooled very quickly, but we see the heavy refractory element, the refractive minerals down at the base, and less refractory sodium-rich plagioclase up near the top. And having this example here, I want to invigorate some thought of how these processes are happening in deeper parts of the Earth, because it is quite likely that there is some intersection of the solidus with the geotherm. And that could give rise to a stratified layer that may, whether this is stable over geologic time is another area of discussion. If it's stratified, how long can that layer stay there? There is some suggestion that within LLSVPs that it is essentially stratified. Is that stable? Yes, Quentin.
But it's even a little more complicated than that.
Yes.
Complicated because we actually don't have a good constraint across the mineral melt system there of whether they go up or down.
Exactly. So there's some nice shock measurements recently on a silicate solid solution with iron, calcium, and magnesium. These are results that came out of the shock lab at Caltech, part of Claire Waller's thesis that showed that within chondritic-like compositions that it was very difficult to form a melt that was dense enough to sink. But if you go to more exotic and extreme end member cases, there could be more iron-rich melts that aren't really consistent with at least what folks think of some of the end member compositions. So there is a lot of discussion. Yeah.
Well, and by exotic, you could mean basalt.
That wasn't in that system. That was not sampled, so there was no discussion of that. Of course.
So let's not get too. So it is a very limited compositional subset that looks at. And so, for example, something like a morb would not actually fall in that compositional domain.
Right.
So I just am questioning the use of the term exotic.
Exotic. Right.
So Jennifer, so
Yes.
there are conditions under which you would have melt at the core mantle boundary, or perhaps within the LLSVPs, reasonable conditions in the present day?
So there was a nice talk last week at the Compress annual meeting by Alan McNamara, who showed some dynamic simulations that in those simulations in 3 dimensions show that this is work in progress, that he showed that actually the hottest parts of the evolution of these large low shear velocities are not at the edges. They're more inboard. And so in those cases, there's these are relative values. So they don't prescribe a specific temperature. But what they did look for were where the regions were hot and essentially the thermal gradient along the core mantle boundary. And so I think these are, there's not the only dynamic simulation of these materials, but it was thought for a while that the hottest parts of these LLSVPs were at the edges. And at least from dynamic simulations, at least this particular simulation showed that they were more inboard. Yes.
Jennifer, a question about the question you just posed to us and something you said earlier. So at higher pressures, you made the point that all atoms become more similar in terms of sizes. So does that mean that as you go to higher pressures, the difference between the liquidus and the solidus temperature gets smaller? And so the importance of fractional crystallization also becomes relatively less important?
It could be, yes. I think there's just not enough, there really aren't enough studies. There are only a handful now that have been done in the diamond anvil cell at core mantle boundary pressures, and there really is there's a difficulty in defining the solidus and liquidus from those experiments, although they do make the claim that they are still relatively large. This is for morb and for a more peridotite melt. So they make that claim. And so we've already talked about decompression melting. This was something raised by Michael Manga, and in terms of generating melts, there are ways that we can think of it in terms of either just the normal situation where we don't have an intersection of the geotherm and the solidus, or where the geotherm is raised significantly to intersect with the solidus. This is such an event at the mid-oceanic ridge. In deeper parts, there could be a stronger gradient in temperature that allows for melt to be produced at depth. This is something that we can consider at all depths of the Earth. and that this and this solidus, again, is defined by the system. And so if one has a system such as mid-oceanic ridge basalts and their sediments, their hydrosediments, this could be significantly lowered, as is shown just schematically here, as the subduction proceeds and the devolatilization of the sediments here could lead to a intersection of that geotherm and the melting or the solidus of this system. So, and from many of these experiments and computational work, the lower mantle as an average rock could be considered as peridatitic, although this is making a certain claim about the ratios of magnesium and silicon. So these boundaries are not set in stone. This is based on experiments that are done on this particular system of olivine, garnet, and pyroxenes as found in peridatites, like the San Carlos olivine nodule. I'll show you as an example. It is possible to generate or to have a system that has a little bit more olivine or a little bit less olivine. And that is a topic of discussion, especially for the transition zone, where the seismic gradients are significantly higher than they are in the upper mantle and the lower mantle. And then as we go down deeper, we see the formation or the dissociation of ringwoodite into the oxide and the bridgemanite phase. And as this is going on in the transition zone, actually at shallower depths, the calcium silicate perovskite phase is exsolving out of the garnet phase. And then we get down to a post-perovskite phase in the D double prime layer. So showing a few examples of these phase diagrams, here I show the fosterite phayolite solid solution phase diagram. It starts at low pressure and goes up to just the shallow part of the lower mantle. This is a fairly well-studied system at lower iron concentrations, where we think the Earth's upper mantle falls around 10 to 12% iron, and that going through these loops, remember that if the system is not disturbed, then it will have a finite width to that transition, which could help in interpreting seismic discontinuities. So we'll get to that example in just a second. But on the right, I show just the magnesium end member phase diagram, where we see the simplification of the olivine, wadsleyite, ringwoodite phase transitions. But we know in the mantle it's not pure forsterite, it's not pure iron-free end member. And so we must think of these systems as having at least finite phase loops. And having finite phase loops, for the olivine system, this was one of the very exciting parts of experimental mineral physics, was the observation, the discovery of the densification of olivine, and that occurred at just about the conditions that the seismologists were observing strong reflections around 400 or 410, which is shown here. And those are the vertical lines here, which is this is a review article by Frost. And then as we get to higher compressions, see these are the Clapeyron slopes of these phase transitions, and these are all isolated tetrahedra. But when it goes into the bridgemanite, it becomes a network of tetrahedra, of octahedra, sorry. So it actually goes into an arrangement that just doesn't have as many degrees of freedom. And that could help one understand the change in slope. Now it's slightly negative. There's some very nice experiments done by Dan Shim, that's this line right here, that showed that this was indeed happening around the 660 kilometer discontinuity. And so that's in a system that's, if we only think about olivine, of course the Earth, I mean, that if it makes up at least 50% of the mantle, it's definitely a good, a very valid explanation for those seismic discontinuities. But in terms of mass transfer and how those discontinuities change in their width and their location depend on the coexisting phases. So we know there is also a garnet system, or if we look at the pure MgSiO3 system, this is not in the presence of aluminum garnet, but it does form a dense structure called majorite. And at low temperatures, it trajects along this Akimotoite phase. And it's possible that this is present in subducted slabs. But now when we think about the whole system, it's simply not just olivine, right? And so these phase loops, they depend on, if one just takes them at face value, then one is asserting that there's no iron exchange in the system. In the presence of garnet, actually, what's been shown is that the iron, the ringwoodite tends to suck up a little bit of that. Not all of it, because there's some equilibrium between the two, right? But it sucks up a little bit of it, enough so that it could sharpen up the boundary, right? If it moves over to the right, we are going through this phase loop. Now it's talking to majorite, and majorite's saying, okay, fine, you can take some of my iron. And then ringwoodite is essentially now finished with its phase loop at a shallower depth. And this could sharpen up the transition. This could be, I mean, there are several lines of discussion about this, but it could be a reason why the 520 is observed in some areas and not in others.
Could you re-elucidate what do you mean by phase loop?
This region here. So this region here is analogous to that solid-liquid loop I showed earlier. But this is an olivine and Wadsleyite loop. So instead of one thinking of it in terms of just the general phase diagram I showed earlier where it was solid and liquid, this is Wadsleyite and olivine. And then likewise, this phase loop here is the coexistence of Wadsleyite and ringwoodite as it's compressed. And this is at 1600 centigrade. Okay, so moving forward, I wanted to show this nice computational result by Lars Stixrud and Carolina Lithgow-Bertoloni. And what this shows is that from first principles, and there is some benchmarking that they did at lower pressure in terms of actually plotting the phase boundaries with observed experiments. I shouldn't say benchmarking. They're actually, derive. They make the claim that's derived from first principles, and that one can see that the trajectory, which is shown right here, this is a density line that's shown here, is that in the transition zone, that they are observing this olivine to Wadsleyite transition in the presence of garnet, and they also have some clinopyroxene that is still stable here. Okay, now the effect of hydration. So I would like to use the word hydration because in many of these structures, at least in Wadsleyite and ringwoodite, they're found as hydroxyl groups. So they're not actually individual water groups, which is different than some of the lower pressure sediments and phases where they have molecular water. And as just as a general trend, this can be more complicated than this, especially in the presence of iron, that it has been suggested that it reduces the transition pressure, and adding another component to the system should necessarily either expand the phase loop, i.e. broaden it, or at least keep it the same. It's unlikely to sharpen it because you're actually adding components to the system. So this scenario, one can plot these the Clapeyron slopes of these phase boundaries, and then actually assess them with respect to different geotherms. And so we see that in colder regions, which could be characterized more accurately by a slab geotherm, that the transition is occurring at lower pressures as compared to ambient mantle, or however one wants to define ambient mantle. And so if these transitions, just for example, if these transitions are happening at lower pressures, that means that, of course, then that would make a prediction that in subducted areas that one would observe the reflection at shallower depths compared to 400. These solid lines are just the olivine system. And then the dashed lines are the peridotite with wet composition. Hydrated. It's showing that it could be, well, it's likely to be shallower depths if you have a similar system. Obviously, it will be a little bit different because the hydration will alter the individual chemistries of the phases. But these solid lines are essentially olivine-dominated systems that are dry. So roughly 60% olivine. Okay, so moving forward into, well, just to show the silica system at low pressures, this is a common phase in anywhere from a few percent to perhaps up to 10% in volume of mid-oceanic ridge basalts. And so one should consider this phase, especially because it has extremely anisotropic properties, the stishovite. It's very stiff, but it's also very elastically anisotropic. And in the mid-oceanic ridge basalt system, we see, okay, this is that loop, the solidus liquidus. And this is as a function of temperature. As we increase, so we see a phase assemblage that's similar, at least at low pressures. We'll have a pyroxene and garnet, and then that will transform into the denser phase majorite, clinopyroxene and coesite, then to stishovite, because the silica phase is going through the phase, its own phase equilibrium. So when we think of this schematic representation, we could summarize. Of course, it's always more complicated than this because not every single chemical assemblage has been, say, measured in the laboratory. But one can make some basic general conclusions, and that with temperature, it decreases the transition pressure of olivine and wadsleyite. The presence of iron does affect the width of the transition. It's another component, so it will broaden the transition. And the transition pressure. So this typically decreases, but this is not necessarily observed for every single system in the deep earth. We can make this generality for the olivine system and perhaps the lower pressure phase assemblages. And garnet, it affects the width of the transition. It actually sharpens it near the 520. And when we look at the hydration component, that in many studies it's been shown to decrease the transition pressure. So I have, I think I will go through, this is just one example of looking a little bit deeper and looking at the iron oxide component and the spin crossover, and in terms of discussing how the spin crossover can affect the dynamics of the lower mantle. And I show this image here because it's been thought to explain some of these isolated pockets of ultra-low velocity zones that may not be associated with hotspots. And so going back to the solid solution, we see, at least at room pressure, a complete solid solution of Periclase-Wüstite. And the iron 2+ in the octahedral coordination, as it is in any structure in octahedral coordination, has unpaired electrons. So this is what we mean by a high spin state, is because it's dominated by the high spin direction of the electrons. And at low pressure, you'll see that the crystal field splitting energy is lower than the spin pairing energy. And so that means that it's unfavorable to pair those spins, to pair them up, to bring them down. But at higher compression or at shorter bond lengths, they will pair. And this has also been shown by DFT theories that it becomes more symmetric environment and also denser by a few percent. And so that has an effect on the total density of the system. So in a study that Natalia did using neon as a pressure medium, just show a result that is important for understanding the dynamics and also compositional effects, that using the same criteria to define the spin crossover, it is evident that with increasing iron concentration, the spin transition does increase its pressure. But at higher iron concentrations, we stop at 60%, they become magnetically ordered. And so it's no longer the classic or canonical high spin, low spin transition. And this begs a question about how complete the MgO-FeO Periclase-Wüstite solid solution is at high pressures and temperatures, because it's interrupted by a magnetically ordered transition. But that at higher temperatures, this will broaden up. This is entropy driven. It's more favored to not be in 100% low spin state. And so it's some mixture of high spin and low spin. And then finally, just looking at the Bridgmanite to post-Bridgmanite transition, this is the last example, in that the influence of the Clapeyron slope, which is thought to be positive, actually extremely positive, ranging from 9 to about 12 in some studies, that we can see that if this is indeed happening inside the Earth, and we know what pressure, we know the pressure inside of the Earth very well. We don't know the temperature very well. But in a very simple assessment of this system, because of course it's more complicated, is that dialing in on this D double prime area and the Clapeyron slope of this transition could provide at least a small constraint on the temperature there. So we have a thermometer where we didn't have this thermometer before. The deepest thermometer before this transition was observed was the core mantle boundary, which was an extrapolation from the inner core outer core boundary along an adiabat, assuming a certain melting point of iron and its alloys. And so this led to the suggestion that along certain temperature profiles, one could back transform to Bridgmanite and have these post-perovskite lenses, which could influence the heat flow across the core. Now we know that that is an important constraint, or it is important for us to understand that in light of, say, these variations in thermal conductivity of iron, presence of radiogenic elements. And finally, with this is a nice study of the high pressure behavior of silica, and showing that the phase transition to ciphertite is actually just a little bit higher than that, the post-perovskite that's occurring in Morb. This is done by Goszolski, Shim, and colleagues, and that this can complicate the interpretation of seismic observations. It's no longer the single reflection that could be the sole cause could be post-Bridgmanite. There are multiple transitions happening in this region. And finally, I just want to end with this figure showing different petrologic assemblages, that we shouldn't, of course, limit our thinking to a peridotite system, the Morb system, the sediment system, which can deliver very hydrous phases to great depth, and that each of these phases have their own personalities. And they could help explain, for example, the seismic velocity anisotropy. But because they have their own personalities and many of them are quite anisotropic, of course they have variations in thermal conductivity, not just between the phases, but within the phase, because they could be, for example, an orthorhombic, they could be characterized by orthorhombic symmetry, like Bridgmanite and post-Bridgmanite, but depending on their interconnectivity, meaning are they sheet structures or are they an interconnected network, they could give rise to very strongly conductive layers if aligned, which is argued for post-Bridgmanite, post-perovskite, along that sheet layer. And so that's what I'd like to end with, and be happy to take some more questions.
Jennifer, what happens to what are the various phases that are stable for Morb compositions at 2,000 kilometers and deeper? All these question marks are exciting. What's down there?
Well, there are some studies that fill in these question marks. In this review paper, it was they're I think probably being a little bit candid there. So this whole phase assemblage down here was investigated in that Goszolski study, and the interesting finding in that study was that the assemblage, which just contains denser forms of those phases, that transition to the denser post-perovskite, post-Bridgmanite layer is at shallower depths than in a peridotitic system. And perhaps Dan can comment on that.
Because it's a 2015 paper, right, that you took that figure from? The review, the next slide?
The question mark slide.
Yeah.
Yes.
My personal view on that plot is pretty outdated, miserably for Morb. It's not just our group, but there are 3 or 4 more groups that actually went down to the core mineral boundary for Morb, and mineralogy is remarkably consistent throughout the experiment. So my short answer to your question is that down to the core mineral boundary, that mineralogy stays the same, but some of them individually go through the phase transformation.
Like stishovite?
Yes, like stishovite, also post-perovskite transition appears to occur shallower depth than bulk mantle. And that is little different between the studies, but the basic picture of 4 different minerals with roughly similar content remains to be more or less true through 4 or 5 different experiments until the core mineral boundary. So I don't know why they put the question mark there, but to me, following the literature, there's no question mark over there. For the sediment, I would agree with the schematic view, but the problem is there are many different possibilities for the composition of sediment that goes into the mantle. So we experimentalists don't know which system to study first. Morb is simpler because there's a better consensus about the bulk composition. Yeah.
But, sorry, I missed something. You said there's a deeper post-perovskite line.
So for calcium silicate perovskite, it stays just stable. And aluminum phase, those are minor phases, so it's sometimes very difficult because it goes down below the resolution limit of technology that we use. Perovskite, our results shows that the post-perovskite transition happens about 100 kilometer or 200 kilometers shallower than what is expected for the prototype.
This transition.
Yes.
In this system.
Right. And for stishovite, there's a well-known phase transformation. There's a slight difference between different studies, but there's a good consensus that stishovite undergoes transformation before core metal boundary.
Yeah.
Use that to map out where there's salt, where there's peridotite in the deep metal, right?
Well,
yeah, that could
that's what we try to argue in the paper, but no one followed up. So hope seismologists can take advantage of that.
Yeah.
Well, this is a question for Jennifer, but maybe also for Dan. Can there be post-perovskite at the bottom of the LSVPs with these large clapeyron slopes, or does it totally depend on the depth and composition?
I think based on the thermal profiles of these LSVPs that it seems unlikely that it would be at the base because the temperatures, I mean, from the 3D study, just a recent study, the one that Ellen McNamara showed, that yes, there are these pockets that are the highest temperatures. Those are inboard from the LLSVPs. But even under, because if there is a chemical anomaly, so if these are modeled as chemical anomalies, they will heat up. They will heat up more than the rest of the mantle. Of course, it would be lovely to have a thermometer and just place it down there, and then we could say it's there or it's not there. Well, not a thermometer. We just go down there and look. But judging from the clapeyron slope, it's unlikely.
So does that mean that we could still see it in the colder regions outside of the LLSVPs? Because there's another component to it, which is anisotropy.
Right.
And there is some evidence that we can see at least more anisotropy in the cold regions, like the ring around the LLSVPs, than inside the LLSVPs.
Right.
And you haven't talked about anisotropy, but post-perovskite, as I understand it, has stronger anisotropy than bridgemanite.
Yes, but as we consider more more scenarios that would be consistent with subduction, for example, morb, there are other phases that one should consider as being sources of seismic anisotropy. And so this is something I think that really should be investigated more, because for example, post-bridgemanite, that anisotropy is based on only calculations. So it could be less anisotropic. It could be more anisotropic.
But then you have to consider the proportions, right? Because seismology can only see averages, right? And so it's dominated by the more abundant components, right?
Unless they are extremely anisotropic. So I think one has to do that calculation to rule out certain phases. For example, the silica component, which is extremely anisotropic, at least at low pressures. The behavior of these. I mean, one thing that one can put question marks here is not necessarily the phases, but the anisotropic. The elastic anisotropy, the single crystal elastic tensors of these phases, only a few have been actually experimentally measured. Many have been calculated, bridgemanite, post-bridgemanite. I mean, all of the phases, actually, most of them have been computed from first principles. And so I think this is a tractable problem, because the only way for us to, how does one induce that anisotropy? First, it has to, which I think will be covered in the rheology talks, or in terms of developing fabric. First, the system has to develop fabric. And then that system has to have anisotropic components that propagate the shear, for example, the horizontally polarized shear wave faster than the vertically polarized shear wave.
Let's thank Jennifer. It's coffee. Rudy will have the last question.
Last comment. Now, isn't the post-station wide, so SiO2 isn't that cubic?
Correct.
And so it would have a much lower anisotropy.
Oh, not necessarily.
Orthorhombic. And is it anisotropic?
Yeah, and cubic systems we know can be strongly anisotropic, like MgO, for example. Yes. Yes. Thanks, Chris.
For each of these categories, these three categories, what's the approximate mass fraction?
Instead of volume fraction, you mean?
So no, I don't mean. I mean, if you were to take pyrolite, morb, and sediments and talk about
yes.
the mass fraction in the mantle.
Okay, so the sediments. So just back of the envelope calculation, it would have to. So it depends on. We should do this, or perhaps somebody already has done this. Is that based on subduction history? How much slab material, meaning, let's say, how much of this 8 to 12 kilometer thick mid-oceanic ridge basalt is subducted into the earth over time, compared to the sort of the crystallization. So this is thought to be the result of the crystallization of the earth, but that is also argued about in terms of its exact chemistry and proportion. And the sediments are, a very thin veneer, but yet they probably contribute a lot to mechanisms of flow, I think, because they definitely are more anisotropic in their bonding environments and also in their hydration content. So,
maybe a question to follow up on here at CIDER.
I think the answer is that it's a lot, a little, and very, very little in terms of volume.
Yeah.
But that doesn't correspond to significance,
right.
as you say, because
right.
particularly the volatiles could play a huge role.
Right.
I would come back to the question of what is in LLSVPs. They are not amorphous, massive structures as far as we can tell. And we've seen internal structure that's compatible with one or more multiple phase changes. They haven't been explained. They're probably difficult to reconcile with silicon. The shallowest of them might be. So at this point, I'd say that there's not much confidence in saying that post-perovskite doesn't exist in LLSVPs or that other things may or may not exist. But there is complexity seismologically. And I think it's fair to say there's no consensus, but there's structure. And understanding that structure may be key to understanding the internal dynamics of the LLSVP.
Yes. Couldn't agree more.
So it's time for us to take a short coffee break, but